Alright, let's break down Einstein's special theory of relativity into simpler terms and explore its fascinating concepts like length contraction, time dilation, and mass variation. Published by Albert Einstein in 1905, this theory revolutionized our understanding of space, time, and motion. It's special because it deals with the specific case where gravity is not significant. It contains two key postulates. Number 1, the principle of relativity. The laws of physics are the same for all observers in uniform motion relative to each other. Number 2, constancy of the speed of light. The speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or observer. Now let's talk about its fascinating concepts. Number 1, length contraction. Objects contract in length along the direction of motion as they move close to the speed of light. Imagine a spaceship traveling at 90% of the speed of light. To a stationary observer, the spaceship appears shorter than it would if it were at rest. However, to someone inside the spaceship, everything would seem normal. The length contraction is not noticeable within their own frame of reference. Number 2. Time dilation. Time passes slower for objects moving close to the speed of light compared to those at rest. Think of a clock on a fast-moving spaceship. If you're observing from Earth, the clock on the spaceship seems to tick slower than a clock on Earth. This is famously illustrated in the twin paradox, where a twin traveling at near light speed ages more slowly than their twin on Earth. Number 3. Mass variation, relativistic mass. As an object moves faster, its mass appears to increase from the perspective of a stationary observer. For example, if a car could move near the speed of light, it would seem to have a greater mass than when it's at rest. This doesn't mean the car is physically changing, rather, its increased mass reflects the increased energy required to accelerate it as it gets closer to the speed of light. These effects, length contraction, time dilation, and mass variation, are not noticeable in our everyday life because they only become significant at speeds close to the speed of light. There's no universal frame of reference. If you're on a train moving near the speed of light, you won't notice anything unusual about your own motion or the space and time around you. It's only in comparison to an outside, stationary observer that these effects become apparent. Imagine you're on a superfast train moving close to the speed of light. To someone standing outside, the train looks shorter, your watch seems to tick slower, and if they could measure it, you'd seem heavier. But inside the train, everything feels normal to you. This is what the special theory of relativity tells us about the nature of space and time at high speeds. These concepts, while hard to observe in everyday life, have critical implications in fields like astrophysics and technology, particularly in understanding the universe and developing GPS systems, which must account for these relativistic effects to be accurate.